All right. In this video, we're going to be looking at applications of the first derivative. Basically, increasing, decreasing, relative maximum, relative minimum, critical points, mean value theorem, and a little bit of particle motion. It's going to be a lot of stuff here. Okay. So we'll start with the definition of a critical point. A critical point of a function is an x value where either the derivative is equal to 0 or the derivative doesn't exist. So f prime is undefined. Right? So what you want to do on your little graph that you've got sitting in front of you, or if you're watching at home, just think about, on this graph, where are the critical points? How many are there? Okay, so I'm going to, freeze the screen for those of us sitting in class. Those of you watching at home, I guess you're just going to watch me kind of fill in the critical points, and they'll have more to say about these critical points in a moment. All right, there they are. Okay, so I found 3 of them. Places where the derivative was 0, where the derivative was undefined. Okay. Now at this first one, maybe I'll call these A, B, and C. Okay, at points A and C, the derivative is equal to 0. But at point B, the derivative is undefined because of the sharp corner, right? Now what I'll say about, I'm not going to write this down, but I'm going to just mention that f prime of x equals 0, that's going to be a place where the tangent line is horizontal. That's points A and C. And for f prime being undefined, that can take a number of different looks. You can have the sharp corner, like at point B. You could have a point of discontinuity, which this graph does not have. This is a continuous function. Or it could be a place where there's a vertical tangent. Okay, all of those are going to be places where the derivative is undefined, which would make them all critical points of the function. Now, what we're going to see is that at some points, at some critical points, you can have a relative extremum. You see here, at point A and f of A, you have like a little maximum. It's at the top of the hill, so to speak. Okay, it's not the maximum because you can see that f of x is going to continue to grow as x gets more and more positive. So, but we'll call this like a local maximum or a relative maximum. And in the same way, at point B and f of B, okay, we're going to call that a local minimum. This year I've decided I'm not going to, give you a definition of local max and local min because I think your intuition will be good enough. And the definition of it, it might not mean much to you. Basically, it's that for a local max, that f of x is less than f of a for x values near a, whatever near means, okay, which is something that you would probably more strictly define in a higher calculus course. So the point I'm trying to make here is that local extrema occur at critical points. Now, oftentimes critical points are local extrema, but not always. Look at point C. Okay, that's not a maximum or a minimum. It was just like it stalled out. It decided to relax for a second before increasing again. Okay, that's neither a local minimum nor a local maximum. And we'll have plenty of examples of that happening, here in a few minutes. All right, now let's do an example. Find the critical points of the function f of x equals 3x to the 4th minus 4x to the 3rd. All right, well, the steps are going to be, find f prime, and then we'll solve f prime equals 0 and f prime doesn't exist. Okay, I'll tell you f prime's always going to exist because that's a polynomial. But why don't you all try that on your own? If you're watching this video, you should definitely pause right now because in like 5-10 seconds the answer is just going to pop up. Okay, there you go. Okay, what I did was I took the derivative using the power rule. That's 12x to the third minus 12x squared. I set it equal to 0, and I solved by factor. Okay. So either 12 equals 0, or x squared equals 0, or x minus 1 equals 0. Okay, so that gets me x equals 0 and x equals 1. All right. Now this one is a little trickier. Normally I would do one example and have y'all do the next one. And, maybe I would have been smart to do this one first and give you the easy one second. But I'm going to do this one for us. This one's got a little bit of trickery going on. So find the critical points of the function. Okay, well, I'm going to need to take the derivative. That's first order of business. Okay, I'm going to use the power rule. I'm going to bring the exponent around the front. That's 2/3 of x to the reduced to the power by 1. 2/3 minus 3/3 is negative 1/3. Plus, the derivative of 2/3 of x is just 2/3. And I'm going to rewrite this. I'm going to write this as 2 over 3 times the cube root of x plus 2/3. But I know that eventually I'm going to have to find out where this is equal to 0. So I'm going to just right now go ahead and get myself a common denominator. Right? I'm going to multiply by a clever form of 1, so I'm not changing the thing. I'm just getting it to have the same denominator. All right, so if I want, I'm just going to rewrite it one more time by combining the things with the common denominator. 2 plus 2 cube roots of x divided by 3 cube roots of x. And I'm interested in where that is equal to 0 and undefined. All right, let's start with undefined. I think that's a little easier. What value of x is going to make this undefined? Yes. Oh. No, it already had the 3 denominator, right? I took the 2/3 and gave it, but yeah. Okay. At what x value is g prime going to be undefined? 0. Yeah, we can't divide by 0. Okay, so g prime does not exist. That's x equals 0. All right, and g prime equals 0. Well, that'll be any time where the numerator is equal to 0 while the denominator is non-zero. And so just as long as we don't get x equals 0, we'll be fine. But we already know that x equals 0 is a critical point. So I'm going to look at the numerator. I'm going to say 2 plus 2 cube roots of x is equal to 0. And I'm going to start solving at x. Okay, I'll cube both sides. And negative 1 to the third is negative 1. So my critical points, that was the instructions, are x equals 0 and x equals negative 1. All right, now let's talk about increasing and decreasing. Now I'm just going to warn you, for those of you watching at home, and I guess if you're sitting here in class, the definition that we're going to take of increasing in this class is probably not the best definition of increasing, but it is going to be the easiest for us going forward, and with the level that we have to go to in this class, it's not going to cause any difficulties. Okay, really, increasing should be bigger x values cause bigger y values, at least locally. But what we're going to do is we're going to say, here, let me draw you a curve that's definitely increasing. Okay, what is going to be true about the slopes of this curve at a place where it's increasing? Positive. Yes, that's what we're going to say. F is increasing when f prime is positive. And in the same way, maybe I could do something that looks like, water slide or something. Clearly decreasing, though. What could you say about the slopes? Yes, that's what I was thinking. Yes, negative. F prime is negative. Okay. Now, these are the definitions that we're going to take of increasing and decreasing. Okay. So in this class, when you see increasing, you can think positive derivative, and when you see decreasing, you can think negative derivative. And that's this concept of increasing and decreasing is something we're going to come back to the entire year. So let's just go ahead and jump right in. Okay, for example, we're going to find the intervals over which f of x is increasing. All right, first things first. We just learned what increasing means. I'm going to grab this, and I'm going to say I need to be concerned with where f prime is positive, where the slope is positive. All right, so the first order of business is going to be take the derivative. All right, we could do that. It's going to be 3x squared plus 6x. Okay. Now we're interested in where f prime is positive. So what we want is we want 3x squared plus 6x to be greater than 0. It's like, wait a second. How do I solve an inequality that's got an x squared in it? Okay, now I've got my preferred way of solving a polynomial inequality, but it might not be yours. So I'll show you both of the ways that I see it, and you can choose your own. Okay, if you were in my pre-cal, I had y'all get a sketch of the graph of this thing. Okay, but regardless of if you're going to make a sign chart or if you're going to sketch the graph, you got to find the zeros. So we're going to factor. We're going to take out a 3x. We're going to be left with an x plus 2. Okay. So this is a second-degree polynomial with a positive leading coefficient that has zeros at x equals 0 and x equals negative 2. So I'm going to come in here. I'm going to make a little number line. Then I'm going to actually make another little number line for people that like to make a sign chart. Okay, people that came from Calculus AB last year, you probably like to make a sign chart. That's great. If you want to keep doing that, go ahead. I personally like to draw a picture of the graph of this thing that I'm going to highlight in gray. And, okay, so this thing is a second-degree polynomial with a positive leading coefficient with zeros at negative 2 and 0. Okay, well, I know what a second-degree polynomial looks like. It's a parabola. And if it's got a positive leading coefficient, that means it's going to open upwards, right? So I can do that. I'm going to draw myself a second-degree polynomial with a positive leading coefficient. Okay, I kind of got cut off. Leave myself enough room. And I can see that this is increasing, as in the derivative being positive. This is a picture of the graph of f prime, right? I can see that this is happening over here and over here. So that's going to be when x is less than negative 2. Potentially also when x is greater than 0. All right. Maybe you're like, dude, I'm not sure about that. I learned how to make a sign chart in pre-calculus or Algebra 2 or Calculus AB or something, and I'm going to keep doing that. That's great. I'll show you how to do that as well. I find that this one, if you're prone to making arithmetic errors, you're going to want to make a graph. If you're not good at sketching the graph of polynomials, you're going to want to make a sign chart. All right, so what we're going to do is we're going to choose a representative from each subinterval. So we're going to choose a number between negative 2 and 0. Okay, what should I choose? Negative 1, for sure. Okay, I'm going to choose something bigger than 0. You could choose 100 if you liked. Okay, because that's the whole thing, is that the only time we're going to have a sign change is at one of the zeros. Okay, so you could choose 100. Maybe I'll choose 100 over here, and I'll choose negative 3 over there. Right, it really doesn't matter. Okay, then we're going to plug it into the formula for f prime, right there. Okay, so 3 times negative 1 is negative 3, which is a negative number. Then negative 1 plus 2 is a positive number. So since I've got negative times positive, that is negative. Okay, maybe this time I'll plug in 100. 3 times 100 is certainly positive, and 100 plus 2 is also positive. So positive times positive is positive. Then on the far left, I'll take negative 3. 3 times negative 3 is negative 9. Times negative 3 plus 2 is negative 1. That's negative times negative, which is positive. So notice how we're getting the same thing regardless of if we use the sign chart or if we sketch a graph. Okay, I'm interested in where this thing is positive because I want to know where it's increasing.
What about negative 1?
All right, question as the bell was ringing for lunch was, what about at x equals negative 1/2? Like something, maybe I'll pull out, pink or something. Something like right there. What about there? Isn't it increasing there? And yes, f prime is increasing there, which would mean that f's second derivative would be positive. We're not talking about the second derivative today. We'll go into that. We're interested over intervals that f of x is increasing. And really what we need to think right there at the point I've highlighted in pink is that the derivative is below the x-axis, which means its y value is negative. Okay, so the derivative is negative, means the function is decreasing. But that was a really good question. I like that. Okay, and then the other thing I'll say about this example, I've been really long-winded about it, is over here on the sign chart, you know, if you wanted to write it in interval notation, that's cool too. You could write that as negative infinity up to -3, or as union 0 to infinity. Okay, you could even include -3 and 0 in your interval if you wanted, because different people take different definitions of increasing and decreasing. Nobody's ever going to be upset about that. All right, next, let's do one involving some trig. Let's find the intervals over which g of x is decreasing. Okay, well, I know what decreasing means. That means that the derivative is going to be negative. Okay, so I'm going to say that is g prime less than 0. Wonderful. Okay, and now what I'm going to do is I'm going to go over here, and I'm going to take g prime. Okay, g prime of x, the derivative of 1 is 0. The derivative of negative cosine would be positive sine. Leave the inside the same, and then multiply by the derivative of the inside. Okay, and now I'm interested in where this is positive and negative over the interval 0 to 6. Okay, and this is where I'm just going to, graph the thing. Okay. But regardless, we need to think about where this is equal to 0. Okay, so I'm going to just draw a little unit circle and think about where on the unit circle is sine coming back 0. It's here at 0 and pi, and I suppose 2 pi also. So to get 0, we'd plug in x equals 0. To get pi, we'd be plugging in x equals 3. Say it's that. And then 2 pi would be where x equals 6. Okay. And if you wanted to make a little sign chart, plug in 1 pi over 6 and 5 pi over 6, that would work. Or you could just, if you know the shape of the graph of sine, you could say, okay, it kind of comes from the origin, it goes up for a while, and then it comes back down, and then it eventually comes back up. Right. I'm interested in where g prime is negative. Well, that's going to be here, what is looking like between 3 and 6. So I'm going to conclude that 3 is less than x is less than 6. That doesn't really look like a less than. And then, but, if you're a sign chart person, I'll go through that. Maybe you choose 5, and maybe you choose 1. Okay, well, g prime of 1 is equal to pi over 3 times the sine of pi over 6. Well, pi over 6 is right there, and, well, oh, pi over 3, whoops, yeah. Pi over 3 is up here, still in an area where sine is positive. And then g prime of 5, so I've got positive through there. And I've got g prime of 5 is like pi over 3 times the sine of 5 pi over 3. 5 pi over 3 is down there. That's where a place where sine is negative. But you see that that's what we're seeing on the purple graph, right? It goes positive, and then it goes negative. And if we're interested in where the derivative is negative, okay, I did not do a good job of labeling my graph. That's g prime, the derivative of the function g. If we're interested in where g prime is negative, where g is decreasing, that's going to be between 3 and 6. Okay, now we're going to talk about how to definitively determine whether you're looking at a relative maximum or relative minimum. How we're going to explain our reasoning when asked to justify our answer. I forgot what the other prompt is. Show the analysis that leads to conclusion. There's another one. We know them. All right. If f prime goes from positive to negative, well, let's unpack that statement. That's f goes increasing to decreasing, right? If f prime goes from positive to negative. Okay, f goes from increasing to decreasing. Well, that's looking like a relative maximum. X equals c would be a relative maximum. Okay, and then if f prime of x goes from negative to positive, well, that's f going decreasing to increasing. well, go from decreasing to increasing. All right, decreasing, increasing. That is looking like a relative minimum. Okay, so, oh, yeah, I fill that in. X equals C is a relative minimum. I guess really probably best if I said is a relative minimum on the graph of F, but you know, I'll know what you mean. All right, for example, and this is going to be a pretty common type of problem like on the homework. Find the critical points of the function, determine if the points are relative maxima or relative minima or neither, and give a justification. Okay, give a reason for your answer. Well, the first thing we're going to do is find the critical points, and we'll do that by taking the derivative and setting it equal to 0, since it's polynomial. All right, so f prime of x is going to be equal to 1x to the 2 minus 8x plus 7. Oh, that's convenient. Okay. I'm interested in where this is equal to 0. But this thing is very factorable. So I'll say 0 is equal to x minus 7 multiplied by x minus 1. Yes. All right. So this happens to be at x equals 7 and x equals 1. Okay, these are my critical points. But I'm interested in determining if these are maxima or minima. So what I'm going to do is I'm going to, maybe give a little sketch of the graph of f. If you want to make a sign chart, good for you. Okay, it's going to have zeros at 1 and 7. And it's going to... it's going to go like that. Okay, and so we'll have actual zeros there. All right, so from x going from negative infinity all the way up to 1, f prime is positive, meaning f is increasing. But then from 1 to 7, f is decreasing because its derivative is negative. And then from 7 on, it increases. But we know that the graph of a third-degree polynomial with a positive leading coefficient oftentimes will look like that. It'll increase, decrease, then increase again. So that should kind of make sense. Okay, I'm going to get rid of that so I don't confuse anybody. And what I'm going to do is I'm going to, give a little bit of analysis. Okay, since f prime is going from positive to negative at x equals 1, that's going to be a maximum. So we'll call that a maximum. Oh, yeah, whoops. All right, we can move that. There we go, much better now, right? Okay, maximum because f prime goes from positive to negative. Okay. Guess you probably wouldn't need to say add x equals 1. Oh, no. Update my background app setting. Just go away. Yeah. All right, and then at x equals 7, well, that's going to be a minimum because f prime goes from negative to positive. F goes from decreasing to increasing. All right, now one for y'all to try on your own. Okay, so if you're sitting in my class, I'm going to ask you to do the exact same thing that I just did. Since f is a fourth-degree polynomial, its derivative is going to be a third-degree polynomial, so there's going to be a little more intrigue. But if you're watching at home, you need to pause the video because, in a few seconds, I'm just going to come with the answer. All right, there you go. So I took the derivative, I factored it. I saw that it's going to be a third-degree polynomial with a positive leading coefficient. It's going to have zeros at x equals 0 and x equals 3, but at x equals 0, it's going to bounce because of that even multiplicity. Okay. So if I'm looking at x equals 0, well, what do y'all think about? Is it a maximum or a minimum? What do we think?
Neither.
Neither, yeah. It ain't going to be a maximum or a minimum because there's no sign change in f prime. Okay, so again, I'm forgetting to label my function. It's neither. right? And the justification, I would say, is because there wasn't a sign change in f prime. All right, then what are we seeing at x equals 3? A relative maximum, relative minimum? Neither. Yes, a min. Okay, yes. Relative minimum. Okay. And for the justification, I would say because f prime goes from negative to positive. All right, here's one where they give you f prime, so you don't have to take the derivative. And it's already factored for you. That's just wonderful. And we're going to need to either make a sign chart or a sketch of the graph. And we'll determine if the critical points are relative maxima, relative minima, or neither. Well, I can tell you right now what the critical points are going to be. It's going to be x equals 0, x equals 1, and x equals negative 4. All right, and I'm going to give a sketch of the graph of f prime. All right, so the zeros are negative 4, 0, and 1. And this sketch that I'm going to draw right here is definitely not going to be drawn to scale, right? Nothing I draw in this class is really ever drawn to scale. Okay, first question. What's the degree of the polynomial? 6. Yeah, there's 3 powers of x plus 4, 2 powers of x minus 1, and a power of x. That adds up to 6 total powers of x. The leading coefficient is going to be positive because if I were to expand it out all the way, I would just end up with 1x to the 6th. You can kind of see how that would happen. So, in some sense, it's going to be like an upward-facing parabola, right? It's going to come from above, it's going to go up at the end, and it might have some weird stuff happening. And I think there might be one too many wiggles. Or maybe not. Maybe that's just the right number. Either way, it could look like that, or maybe it doesn't, because of something else happening. All right, what's happening at x plus 4? That 3, that triple root, what's it causing? How would you describe it? It's a bend. Oh, I like that one. I haven't heard that one before. Maybe I have. I don't think I have. It bends through. It hesitates before it does pass through because it's an odd multiplicity, but it's hesitant. Okay, and then at x equals 0, since it's a single root, it's going to pass through confidently. And then at x minus 1 squared, whoops, excuse me. At x minus 1 squared, that's going to cause a bounce. But even still, you would kind of know that if you knew the end behavior of a 6-degree polynomial with positive coefficient. Okay, regardless, I'm going to do the easy one first. X equals 1. Neither because of a lack of sign change. Okay, I'm going to remember to label that f prime. Eventually, I'll remember to label these. Okay, let's see. Rather than asking you about a specific point, maybe I'll ask you, which one is the relative maximum? X equals negative 4. Yes, okay, it's a relative maximum because f prime goes from positive to negative. And at the same time, I'll say x equals 0 is a minimum because f prime goes from negative to positive. And if you're having trouble remembering, just translate it into increasing, decreasing, right? F prime goes from negative to positive means f goes from decreasing to increasing. Then in your mind, you can envision a thing going from decreasing to increasing, and then you can see in your mind that is, in fact, a minimum. And I don't really like how that's organized, how that looks, so I'm going to give 3 bullet points to make it look a little better. All right, let's move on and do another one. All right, graph of f prime is shown below. Find the critical points of f. I can do that. That's places where f prime is 0 or undefined. All right, well, here's a place where it's 0. There's another place where it's 0. That's the third place where it's 0. So I've got 1 and x equals 3. That's how we find the critical points. Okay, they're giving us the graph of f prime again, same graph. And they're asking where is f increasing and decreasing. And I think I'm going to let you all try your hand at that. If you're watching at home, pause the video. You know how it is. All right, there you go. So I like to first take it from English to algebra, okay? Increasing means the derivative is positive. Okay, then I kind of colored in red where that happens, where f prime is positive, where it's above the x-axis. And that's between -3 and +1, and where x is bigger than 3. And then the same thing for where f was decreasing. I know that that means that the derivative is negative. And I colored in where the derivative is negative in blue. And so that's where x is less than -3, or between 1 and +3. All right, now I'm going to ask you about the relative extrema of f. Okay, again, you should pause at home. As you're in class, you're doing all the work right now. Just checking your answer with mine. All right, I found the relative extrema. Really what I did was I took all the critical points and I thought about, are we going from negative to positive or positive to negative? And then in my mind, I'm thinking, okay, negative to positive in the graph of f prime is decreasing to increasing in f. So that's a minimum. And you can say the same thing about x equals +3 because, that's the same situation. And then at x equals 1, okay, derivative going from positive to negative, function going from increasing to decreasing, that seems like a maximum. All right, let's move on. Okay, next we're going to talk about the mean value theorem. Okay. So if f is a differentiable function on a closed interval, or really if it's continuous on the closed interval and differentiable on the open interval, supposing it might be only defined on the closed interval, then there is an x value c where, and I'm going to say this in English first, and then I'll put the algebra, definition down, where the average rate of change, which would be the slope of this line, that's pretty good, right, is equal to the instantaneous rate of change. It's got to happen somewhere, if the function is smooth or differentiable, whatever you call it. Okay, where the average rate of change, which I'm saying the slope is, in red. So average rate of change is equal to the instantaneous rate of change, which I'm going to color in blue eventually. So there's somewhere in there where the slope of the tangent line is parallel to the slope of the secant line. It's a different way of saying that. Are you seeing a place where that might happen? If you've got a ruler with you, you could just, I kind of set the ruler on that secant line, that red line, and slide it until, yeah, I'd say somewhere between 4 and 5-ish. Now this is, and 0, I think, is pretty close, I think if you actually went at 0, it'd be a little too steep. But I'm attempting to draw a tangent line, using a tablet and a pen. It's not that easy. If I was actually using paper, under the document camera or something, I would get out a ruler and I would, slide it up so it's parallel. Okay, so I'm going to attempt, that looks pretty parallel to me. That looks great. And I don't know if it's going to look good on the video, but whatever. And then over here, maybe something like that. Okay, so this one had 2 places because it had 2 turning points between on the end. Okay, and the way that we write this is that f of b minus f of a over b minus a is equal to f prime of c, where c is between a and b. But the important thing is the idea that the average rate of change must equal the instantaneous rate of change if the function is differentiable. Very important. If the function is differentiable. Now we're going to break that rule here in a second and see what happens. All right, let's talk about if f is not differentiable on the interval a to b. I'm going to draw something like, I might move the y-axis a little bit, and maybe talk about, like maybe absolute value x. between, I don't know, like -3 and +6. And this function is not differentiable because of the sharp corner. And if we go over here and we try to draw a secant line, like there's not going to be any place where the slope is equal to, I guess it rose 3 when it ran 9, so a third. Because I know that on the right side, the slope is 1, and on the left side, the slope is -1. Okay? Mean value theorem does not apply because the function is not differentiable. Okay, let's talk about a different case. All right, if the function fails to be continuous, then it's, certainly not going to be differentiable. And again, this has just got slope 0 everywhere, but if I were to, let's just imagine if I did, connect those 2 points with the secant line, I don't have a place where the tangent line has the same slope as that because of the function not being differentiable. All right, now let's look at the case where f of a is equal to f of b. All right, now in the case that we have a differentiable function where the ending value is the same as the starting value, well, if it's differentiable on a closed interval, we can certainly apply the mean value theorem. And that means that the slope of the tangent line has to be the same as the slope of the secant line, somewhat. But if f of a equals f of b, then f of b minus f of a divided by b minus a, well, it's going to be 0 divided by b minus a, which is 0. Okay? But the mean value theorem tells us that that has got to equal f prime of c for some c between a and b. So basically what it's saying, then there must be a place with a horizontal tangent between a and b. Uh-oh. All right. And this is what we would generally, in a Calculus 1 class, call Rolle's theorem. All right, and the type of question they might ask you about the mean value theorem is, find the value or values of x that satisfy the conclusion of the mean value theorem when applied to f of x equals x squared on the interval -2 is less than or equal to x is less than or equal to 1. Well, basically what we've got here is, okay, first of all, I'm going to remark that f is differentiable because it's x squared, it's polynomial. Okay, differentiable everywhere. So I know that the average rate of change is f of b minus f of a needs to be equal to f prime of c. That's the mean value theorem. For some c between a and b, where a is -2 and b is 1. Okay, well, what we're going to do is we're going to find f of b. F of b is 1 squared is 1. Minus f of a is going to be -2 squared is +4. Divided by 1 minus -2 is something like 3. So 1 minus 4 over 3 is equal to -1. Right? So that means that f prime of c has to equal -1. Well, f prime of x is equal to 2x. Okay, f prime of c equals 2c. So I need 2c equals -1. And that c equals -1/2. So if you went in and you found the slope of y equals x squared at x equals -1/2, you would find that it equaled -1. And that would be where the slope of the tangent line was equal to the slope of the secant line. Okay, here's another probably better example. Find the value or values of x to satisfy the conclusion of the mean value theorem on the closed interval -5 to 3. Okay, well, I'm going to right now just block off -5, -1, 2, 3, 4, -5, up to +3. Oh, well, there we go. They're both 0. Okay, so that's a place where f of b equals f of a. So the places that will satisfy the conclusion of the mean value theorem will be the places where the slope of the tangent is horizontal. This is something I would say like that and like this, which I think is x equals 2 and x equals negative 3. Okay, these are the types of questions I can ask about them. All right, now the last thing I've got for you is some particle motion questions. This is one-dimensional motion, motion along a line. This is really just the very basics of it. Position is the type of thing that if the particle is moving along the x-axis, we'll usually use x of t. Sometimes people will use s of t, but I don't like that all that much. And that is oftentimes measured in meters. Now, velocity is the rate of change of position, right? It's kind of like speed. Now, we'll talk more about that next time. But velocity, we're going to call that v of t. And the way we get it is by taking the derivative of position, right? It's a rate of change, so that would make sense. It's the instantaneous rate of change of position. And, you know, if x is measured in meters and t is measured in seconds, well, the units of the derivative will be the units of the dependent variable divided by units of the independent variable. And acceleration, well, that's the rate of change of velocity. So we could say that's the rate of change of velocity. And as a consequence, we could say it's the second derivative of position. And that's going to be measured in the units of v divided by the units of t. And you might say meters per second squared, but I'm kind of unclear on what it means to square seconds, so I'm just going to leave it like that. Meters per second kind of makes more sense to me. Then I've got some terms that might show up, in a multiple choice question or something, and I wouldn't want you to get caught off guard. I want you to know what they mean. Okay, at rest, it means the thing's not moving. Well, that's equivalent to saying that the velocity is equal to 0. Okay, moving to the left along the x-axis, say, is where the position is getting more and more negative. The position is decreasing. Okay, well, decreasing is where the derivative is negative. The derivative of position is velocity. So this is where velocity is negative. Okay, moving to the right in the same way, position is getting larger. It's increasing, meaning the derivative of position, velocity, is positive. And then changes direction. Well, something's got to change the trajectory. It was moving to the left, now it's moving to the right. It was moving to the right, now it's moving to the left. That's going to be a sign change in v. All right. And now let's look at a couple of examples, and then I'll wrap up this video. It's already gone really. All right, here's one that I don't think is very likely to be asked again or in the future. I certainly wouldn't put it on my test, but the position of a particle moving along a straight line at any time t is given by s of t as t squared plus 4t plus 4. What is the acceleration of the particle when t equals 4? Well, I've got the position. I'll get the velocity by taking the derivative of position, which is going to be, all right, s prime is 2t plus 4. And if I want the acceleration, okay, well, that's, the derivative of velocity, or the second derivative position. Whatever it is, I'm taking the derivative of 2t plus 4 with respect to t. And that's 2. So it didn't even matter, what the value of t was, because acceleration was constant. Okay, so this is b, 2. Okay, so number 21 in your multiple choice packet, it's b, because the acceleration is constant. All right, the last example I've got is number 30 in your multiple choice packet. A particle moves along the x-axis so that at any time t, its position is given by x equals t e to the negative 2t. What values of t is a particle at rest? Oh, I remember this one. This one's good. It comes back with like some factoring. It's a little different. Okay, at rest, to me, means v equals 0. So first I have to find v. V is going to be the derivative of x with respect to t. And I have to use the product rule. Well, I'll take the derivative of t first. That's 1. E to the negative 2t stays the same. then I'm going to add in, leaving t the same, the derivative of e to the negative 2t. Well, that'll e to the thing is its own derivative. And then we multiply by the derivative of the inside, which is negative 2. Okay, I'm going to write this a little differently. E to the negative 2t minus 2t e to the negative 2t. And I'm interested in where this thing is equal to 0. It's like, well, how am I going to solve that without a calculator? This is not a calculator question. What I'm going to do is I'm going to factor. I'm going to factor out that e to the negative 2t. I'll be left with a 1 and a minus 2t. Okay. So if these two things multiply together to equal 0, either e to the negative 2t is equal to 0, or 1 minus 2t is equal to 0. Now, 1 minus 2t is equal to 0 when t equals 1/2. Right? And, you know, e to the 0 is 1. E to the 1/2 would give you e to the negative 1. That's not 0. Really, there's no power of e that's going to come back 0. Okay? The more negative you make the power of e, the closer it will get to 0. But you can't ever solve this equation. Another way of thinking about it is if I did want to solve this equation, I would take the natural log of both sides, and the natural log of 0 is undefined, okay? Because of what I was just saying. There's no power of e that comes back 0. Okay, so this is t equals 1/2 only. And that's all I got for you in this video. If you made it this long, good for you. Right? Just keep practicing.